Okay, so welcome not only students of 252, but also everybody else at Berkeley who's chosen to join us. It's great to see a full house, and I'm standing this close to Dr. Federico Fagin not because we've known each other a long time, but because the mic cable is short. But it's my very, very great pleasure. Thank you. That's a little. My even greater pleasure to be able to introduce Dr. Fagin. Those of you who know me know that besides being an instructor and a researcher here, I have kind of a passion about the history of computing, and there's nothing quite like hearing about the history of computing from someone who really was there during some of the most important moments that kind of lay the foundations for what so much of what we now take for granted. So I'll give a very brief biological sketch, but Dr. Fagin's really been all over the place. Starting in Italy, where he got his degree in physics in 1965 from the University of Padua. He worked for a while at Fairchild Semiconductor in Milan before moving to their R&D facility in Palo Alto, where he invented the first MOS silicon gate technology and brought to market the first commercial integrated circuit using that technology. And then in 1970 and 71, he did the work for which at least I know him best, which is that he was the lead design on the Intel 4004, which I think can rightly be argued to be the world's first microprocessor. Very much of, all of the follow-on that happened during the sort of early years of the PC revolution. Those of you who are about as old as I am might remember computers like the TRS-80, the Sinclair ZX80. Those were based on the Zilog Z80, and guess what? Dr. Fagin was also the founder of, or co-founder of Zilog and the designer of the 8080 at Intel and the Z80. So quite an industrious career, and that's just the part before he decided to move on to other fields. After that, he went on to co-found Synaptics. Synaptics developed the touchscreen technology that is now probably in every pocket in this room. And after that, later in 2003, he went on to found Foveon and do some interesting work in sensing. And most recently, he was telling me he's now got a foundation that is supporting projects investigating the nature of consciousness. So, trying to stick to the easy stuff. It is my very, very great pleasure to have him here. Please welcome Dr. Federico Fagin.
Well, it is a real pleasure to be here today to give you the impressions from a old-timer here about the early days of microelectronics and microprocessors. All right, so let me start back about 100 years ago. The electronics, I will talk about microelectronics, but electronics started with things like this. This was the first triode vacuum tube. It was done in 1906. And it really set the beginning of electronics because it was the first device that could amplify electrical signals. In about 20 years, the triode and other vacuum tubes were found application in telegraphy, radio, phonographs, and so on. And so they really set in motion a tremendous number of new applications. And that number kept on growing. And during war, of course, the number of applications were in telephony, television, radar, computer, servo mechanism, you name it, just about many of the things that we have today. And, but of course, vacuum tubes were very expensive in energy. The ratio between the useful signal energy to the energy that was inputted to the device was a very small number. And people were searching for better alternatives to vacuum tubes. And the first opening to that alternative came in 1947 when the principle of transistor was demonstrated at Bell Lab. And by 1951, the first commercial germanium transistors were marketed. Those are the way they look in those days. And a few years later, the first commercial silicon transistor were invented. They were much better, much faster than germanium transistors. However, they were much more expensive, and so they were not used very much until the planar process was invented. I will say something in a second. But by the late 50s, many military, computers, industrial, and consumer applications using transistors occur. But the invention, the seminal invention that really started contemporary microelectronics was the invention of the planar process that happened at Fairchild Semiconductor in 1959. Fairchild was a startup company. And it was done by Jean Herny, a Swiss inventor who was part of the team of 8 that started Fairchild. With the planar process, you could create transistors many at a time instead of one at a time, as was done before. So that was the fundamental way that opened the way for integrated circuits, because integrated circuits require many transistors you can connect. Well, in a planar process, the transistors are one next to each other. So the step to an integrated circuit is an easy one, relatively speaking, after the planar process. That step was made by Bob Noyce in 1961, also one of the 8 original co-founders of Fairchild. And this is what the first integrated circuit looked like. The basic invention here was a way to insulate the transistors within the silicon wafer. And by 1962, the first integrated circuits were commercially available. This is an RTL, resistor transistor logic gate. That was the first integrated circuit commercially available. So that was 62. Let me take a step back and say a few words about the history of computers, because computers did not come by the way of electronics. Computers came by the way of calculators. You know, they were mechanical calculators, starting with the Pascaline, invented by Blaise Pascal. But basically, calculators did not become a reality until mid-1800. Through that genealogy, computers developed to the point where in 1941, Konrad Zuse, a German, built the Z3, which was the first electromechanical computer. It was a Turing machine complete computer. The interesting thing is that the memory was done with photographic film. Of course, the emulsion was not there, but basically 35 millimeter photographic film by punching holes. So you could make ones and zero by punching holes in a film. And that was working. And then in 1944, in England, they developed the Colossus with Turing was one of the designers of the Colossus. That was used for intercept and decipher messages through the Enigma, which was a basic cryptographic machine that the Nazis used, and certainly helped win the war, Second World War II. The first electronic computer was the ENIAC, although some contest that. But by 1949, we had the first practical store program computer. The ENIAC still used plug boards with cords to program. So it was not yet a store program computer, though it's credited as the first electronic computer. Of course, the Z3 used 2,300 relays. They at a clock frequency of about 5 hertz. So we have come a long way. With the Colossus at Bletchley Park, vacuum tubes were used as switches. Vacuum tubes as switches switch much faster than in 10 milliseconds or so, which was the switching speed of relays. And so the first computer used vacuum tubes. The first electronic computer used vacuum tubes. And they were vacuum tubes until 1959, when IBM introduced the IBM 7000, which was the first commercial computer to use transistor. And by the way, it wasn't until 1951 that you could actually buy a computer, a UNIVAC 1, which cost about $3 million, which is probably equivalent to maybe $24 million today. So they were quite expensive. With the inventions of integrated circuits, of course, we see the size of the computer reduced. By 1965, DEC introduced the PDP-8. It was the first mini computer. The first version uses transistors. So this big cabinet here was full of transistorized printed circuit board. And in '68, the first mini computer using integrated circuits was placed into the market, and it was this box below. So this box below used integrated circuit. It was the entire mini computer. The base cost was $16,000, which is a lot of money. It was about $120,000 today. So they were relatively expensive, but of course not even close to the cost of a mainframe. And in fact, more than 50,000 units were sold, were large computers. Probably if they sell a few hundred, that would have been a very, very good business. So mini computers open up many new applications, particularly in control systems. And at the same time that the DAC PDP-8 was introduced in the market, the Olivetti Programma 101 was introduced. It was designed by a man that I've known, Piercarlo Perotto, and this is the machine. This machine had a computer at its heart. It had a printer, a magnetic card reader, a keyboard, so it was a self-contained programmable calculator that set a new direction in the marketplace. It was really a precursor of microprocessors and PC. And my first experience and my first introduction to computers starts when I study in the Technical Institute in Vicenza, in radio technology. Of course, vacuum tubes in those days were the ways to go. And I graduated in 1960. But I became very interested in computers, as I was in the last couple of years of school. And after I graduated, I worked for Olivetti as an assistant engineer in their R&D laboratory in Borgo Lombardo. In those days, Olivetti was actually quite advanced. In fact, in 1959, they introduced a transistorized computer the same year that IBM did their 7000 family. And it was the Alea 9003. What happened when I was working at Olivetti is that my boss got into a very bad accident, and it was out of commission for many months. And so I took over the design and led a small group that actually built an experimental electronic computer when I was 19 with 4K by 12 bits of magnetic core memory. And when it came back, I was so much into it that it let me do it. So I ended up completing the job. This is the experimental computer. This is me, and this is my technicians with which we design and built. I co-designed about 60% of this machine, and I built it all with the help of those 4 technicians. And it worked. And I was told that this machine was inspired Perotto to actually develop the Programma 101, because it showed that you could build a full computer with a much, much smaller amount of electronics, and you could minimize the electronics by creating sort of micro modules, still with discrete components, which were used in the Programma 101 to create the first programmable desktop calculator. So let's take a look at what happened in the time frame between the invention of the first integrated circuits, or the commercialization of the first integrated circuit, which is 1962, to 1968, the year when I came in this country. The first family of integrated circuits were logic families using resistor transistor logic, RTL. Then a year later, diode transistor logic were introduced in the market. And a year later, the final family that became the standard in the industry, the TTL, transistor logic. The first operational amplifier was the MU-A 702 in 1964, and that was an extremely successful design because in those days, a lot of designs were still analog, and having a stable operational amplifier was a kind of difficult thing to do. The next design was the MU-A 709 in 1965, and the MU-A 741 in 68. And believe it or not, the MU-A 741 you can still buy today. It's still in volume production today. Of course, analog to digital and digital to analog converters from 65 on were become available. Many medium-scale integration functions, meaning chips with hundreds of transistors, were available from 66 on, where you could have half-adders, adders, multiplexer, and so on. And the first commercial MOSICs were introduced by General Microelectronics, a company that started in 63. People that came out of Fairchild, where the basic MOS technology was developed. And their first product was a 20-bit shift register. Then 2 years later, they introduced a 100-bit shift register. Actually, in 67, they even have a 23-chip calculator that was that was done for a American manufacturer. But GME could not really produce MOS devices, and so they ended up being bought out and they disappear. But I took a course in 1966 from General Microelectronics because the company that I work in Italy was was representative of GE in Italy. And so I know, because I tried to buy a 100-bit MOS shift register for a customer, and they could never deliver. So I know that they couldn't do it. And in fact, in 1967, they were bought out and disappeared. But anyways, this is the situation. In '68, nearly all integrated circuits in production use bipolar technology. Today, bipolar technology is practically not known. MOS technology is taken over the industry. TTL, bipolar integrated circuits, dominated the market for the digital aspect of the market, and many medium-scale integration functions were available. And MOS technology was beginning to emerge as an alternative technology for low-speed, high integration level applications, as I mentioned earlier. And Moore's law was evident. Morse made that observation that became known as Moore's law. It's really not a physical law, but is an observation that basically there is an exponential growth. He said in 1965 that the number of transistors for which the cost per transistor was nearly minimum would double every year for about 10 years. The doubling rate, of course, has slowed down quite drastically. Today, the doubling rate is every 3 years or so. But Moore's law has really been quite helpful as a way to look at the progress of microelectronics and to plan for future products. And according to what was understood in those days, large-scale integration circuits, meaning circuits that would have more than 1,000 transistors, would occur soon. In '68, the basic technology for MOS was metal gate. They had high threshold voltage, believe it or not, 5 to 10 volts, 5 to 9 volts of threshold voltage. It was P-channel MOS, and it was in production at several companies. And the MOS business was primarily custom circuits, many for the government, for NSA, for example. Read-only memory and shift register memories were also widely used. And in fact, people that wanted to build a small memory system, they could not use core memories because they were way too expensive for a small system, because the periphery would dominate the cost. And so they used shift register memories made with MOS technology. But it was realized that you could do much better than shift registers by developing random access memories, and that work was going on in '68 at several companies. And it was also realized that MOS technology needed a self-aligned gate, low threshold voltage, and reliable transistor. Transistors were not reliable in those days. In fact, a lot of serious users did not use MOS because their reliability was not at the same level of bipolar technology. So when oh, by the way, let me quickly show how you build a metal gate MOS. There are 4 masking steps, and at the end, the MOS device, you have source, drain, and the gate. Notice the overlap here between the gate and the source and drain. That is where the transistor is much slower than it needs to be, because the overlap capacitance, the stray capacitance, and particularly the drain to gate overlap capacitance, gets multiplied by the gain of the stage in which the transistor belongs, and that slows you down quite drastically. So the best way to solve the problem was with a self-aligned gate. And so let's tell the story of the silicon gate technology, which after some research that was done at a Bell Lab, where 2 engineers at Bell Lab have shown that you could possibly use silicon to make transistors. I joined Fairchild, and that was done in '67. I joined Fairchild in February '68 to lead the development of the first process for making self-aligned gate devices. At that time, Fairchild was considering molybdenum and silicon, and I chose silicon because it seemed to me that it was a much, much better, more compatible with the rest of the process technology that we're using those days. Nobody has been able to build transistors that would be suitable for integrated circuit at that point. So the first thing that I had to do was to create the process architecture that would allow to build integrated circuit, not just show that you could you could do a self-aligned transistor with silicon. And along the way, of course, I had to develop the detailed process technology. I designed the first integrated circuit using that technology to show that it could really be done. And by the end of '68, the technology was ready. And by that time also, the 3708 was commercially available using self-aligned gate. This technology ended up being adopted worldwide. And for 40 years, it was at the core of all the progress in microelectronics. Only the last couple of generations used and moved away from silicon gate because of the need of a much higher dielectric constant oxide. The silicon dioxide is 3.9 dielectric constant. The most advanced technology now use material based on hafnium and other materials, weird materials, to get more like 15, 20 dielectric constant, so that you can maintain the field at the oxide silicon interface as you scale down the size and the voltages of the transistors. But the important point here is that the silicon gate allowed to make a MOS integrated circuit that for the same power dissipation and the same lithography were 5 times faster. You could put twice as many transistors, and they had better than 100 times less junction leakage, so that you could do dynamic memories, for example. You could not do it with metal gate because the leakage was too much. But with silicon gate was shielded, and therefore you could clean up the process very much, and at the end you had highly reliable integrated circuits with the same reliability level that the industry required. So the silicon gate technology really allowed to do all the things that were promised by MOS technology, but they were not yet delivered. It also enabled new device types like CCD for imagers, and EPROMs, which are the progenitor of the flash memory that you now have in your pocket. With metal gate, you could not make floating gate devices that could hold charge for years or for hundreds of years. That's the process for silicon gate technology. You start by cutting out a hole where both drain, source, and gate are going to be found. And then the silicon gate determines where the source and the drain are going to be. So if you misalign the polysilicon over this window, you simply change the shape a little bit of the source and the drain, but you do not change the fundamental aspect of the active device. Therefore, all the junctions are going to be exactly the same, and the overlap is only between the gate and the lateral diffusion of the junction. So with this technology, the first chip that was done was fabricated, and as I said, it was in the market by the end of 1968. These are the 8 big switches. They are analog switches, so they had to have very low leakage. That's why leakage was so important even here, because you have an analog switch, and leakage is just not acceptable. So, and that's the decoding logic. And this device showed that you were 5 times faster, that you had all these characteristics that I've shown you, that I mentioned earlier. The technology was presented in October, at the end of October, in Washington, D.C., and it was also the cover story in a 1969 article on Electronics magazine, which was in those days was one of the most diffused magazines in electronics. So now let's take a look at how computers and microelectronics converged. So by 68, it was recognized that a small computer offers significant advantage over random logic for the implementation of calculators in computer terminals. For example, here is the HP 9100, was introduced in the market in 1968. It basically copied the architecture, but improved tremendously over the Programma 101. It was a scientific calculator instead of more of an accounting calculator like the Programma 101, though the Programma 101 could also do scientific calculation. But this one had, instead of having a serial memory, magneto-restrictive memory like the Programma 101, had a core memory inside, which is, believe it or not, that's a major feat of engineering for HP. It had a magnetic card like the Programma 101. And this continued to show the potential by using a computer at the heart of a calculator of what you could do. And also in 68, for the first time, there was a technology that had the right speed and power and reliability to make a CPU. And that was the silicon gate technology. So enter the BISICOM project. Now, in April 1969, that was less than a year after Intel was started, BISICOM approached Intel because they wanted to convert their into silicon their design for a family of calculators. They had partitioned the system in 7 different chips. They had a special purpose micro-instruction programmable CPU that they thought could be made in 3 chips, a read-only memory, a shift register read-write memory, which is the way calculators were done in those days, and 2 I/O chips. So that was their vision, to make a programmable system and also to reuse the chips for a family of calculators. Now, when Ted Off, who at that time was the head of the application group at Intel, took a look at the project, the proposal, he saw immediately that there was no need to use shift register read-write memory, because in those days, Intel was already working on dynamic RAM. And of course, a random access memory is much better to make a computer than a serial memory like shift registers. And so he proposed a simpler architecture using dynamic RAM instead of shift registers. And that proposal was then refined with the help of Stan Mason, that worked for Ted Off, and Masatoshi Shima, who was the BISICOM engineer. And they partitioned the new architecture into 4 chips. And that was done by October 1969. There was a CPU, what they thought could be done in a single chip, a CPU, a read-only memory. There was 2,000-bit, which was state-of-the-art in those days. A RAM that was about 380 bits or so. That also was state-of-the-art. And an I/O chip. There was a relatively simple chip. And they believed that the CPU could be made in a single chip. But none of the 3 were chip designers, so they did not know how it could be done. There was nobody at Intel that could actually start the project until I was hired, and I joined Intel in April 1970. But what I found was that Intel had absolutely no experience and no infrastructure for random logic designs. Now, random logic design was a pretty well-developed art for MOS in those days. For example, Texas Instrument or Intel, Fairchild, they had a library of cells. They had computer programs to assemble cells into an integrated circuit, even if then the layout was done still by hand, but you could copy the cells that were already developed. They had techniques for testing and special testers and so on. Intel had none of that. In fact, they didn't have, they had very few circuits that were developed for their own memories, but those are very simple circuits. And so I had, I was starting 6 months late with no infrastructure, and they had promised the customer that they would have 4 chips in 9 months, which is unbelievable. I mean, I don't know what they were thinking. But at any rate, maybe the customer put a lot of pressure on them. But at any rate, 2 days later, Masatoshi Shima was coming to check on the progress of the project. He was not told that no work had been done for 6 months. So he comes and says, I'm here to check. And I say, okay, well, what are you checking? I came here just 2 days ago. I know now what I'm supposed to do. But he said, well, logic design of CPU is supposed to be done, schedule. And I said, no, I mean, here's what I have. And I gave you what I have. And he said, I have. What do you mean I have? That's all I have. You bad. He started insulting me that because I was lazy, I didn't do anything. It took me a week to convince him that I could not have done anything in 2 days. So finally calmed down, and I was in the office. It was in the same office, and there were many spirited telephone conversations with Tokyo, and I later was told that they were considering, basically walking away from the project because they felt that Intel was just not a reliable company. But anyway, so eventually I convinced Shima that I was in the same boat. I wanted to do the job, but I didn't have anybody. I didn't have an engineer. I didn't have a draftsman. I didn't have anything. And I was on my own. Intel was a memory company, and all they wanted to do was memories. And in fact, both Andy Grove and Vadez were resenting the marketing, and Bob Noyce wanted this project to go. And but I was caught in the middle, right? Well, I convinced Shima that if he helped me, we could certainly not make up for the delay, because I could not do everything in 9 months, although I would try. But I said it would take about 11 months to do those 4 chips, and if I had the right help, which eventually I got, slowly, but eventually I got. So he basically got permission to stay for 6 months to help me. So the first thing that I had to do was to create the design methodology and the building blocks using Silicon Gate. If Silicon Gate is deceptively similar to Metal Gate, but you actually have to, the layout is completely different. And in fact, the engineers of Fairchild thought that it was not that great in layout because they were using the same mental models and moving their Metal Gate design into Silicon Gate. And so the chips were, the cells were coming out larger than they needed to be. And but because I understood from the inside the technology, I was able to get really the size advantage that was inherent in the technology. But you needed to think differently. The other thing is that everybody thought that you couldn't make bootstrap loads with Silicon Gate because basically there is no junction underneath the polysilicon. And for a while I believed the naysayers, but eventually I figured out a way to do it. And I figured out a way to do it just before joining Intel. So Intel didn't know that. And they thought that they could use a 2-phase design without bootstrap load, which is impossible. It doesn't work. So they would have to use static designs, which cost about 3 times the number of transistors to do the same job. And so it would not have been possible without the bootstrap load. But fortunately, I had just developed and shown that the bootstrap load works at Fairchild, so that was an important invention that made it possible. And also the next invention was the Bury contact, which I had done earlier at Fairchild, where basically you could make a direct connection between the polysilicon and the junction using just one more metal, just one more mask, and without metal. And therefore, you could have essentially 2 layers of interconnection. And that was very important for random logic, because interconnection dominate the area of the chip. I also needed to brush off, and use the graphic design that I had used in my technical high school that we were using for vacuum tubes, where there are no equations, so you had to use vacuum, graphic design. And I used that but using measure MOS characteristics to size the transistor rapidly, otherwise I would have to take much more time to design. So, perhaps one of the most vital differences in the way people were doing things in those days was to combine the logic design with the circuit design and with predictive layout information in a single schematic. And that allowed to have only one document instead of translating from logic design to circuit design to layout. making a much easier and much error-free process. So, for example, this is what a piece of this document looked like for the 4004. Each transistor, if a transistor is shown like a resistor, it's actually not a resistor. It's a transistor that is longer than wider. And so there is a standard width, and the length is shown with a number next to it. And here you have a typical transistor, which is wider than longer, and this also the number is there. And the transistors are roughly, close to where they are going to be in the final layout. Of course, you cannot know ahead of time. But in this way, there will be a guide done by looking looking at the programming the layout from the beginning, so that you know where essentially the pieces are going to be. And this was very, very helpful. So that's how a piece of the 4004 what it looks like. You can see immediately that the pink, orange, that's polysilicon. The silver is aluminum, and so you see that aluminum crosses silicon, and so the bootstrap loads those are the capacitors for the bootstraps load. Those here, and then the interconnections between, for example, this is a Bury contact over here, so metal can go over it. And so with this technique, we have twice the density of metal gate, and of course much faster because of the other characteristic of the silicon gate technology. That's how we could make in 1970, 71, a CPU that was much faster. But a typical integrated circuit in those days of this complexity with metal gate would have run 150, 200 megahertz max, and this run 750 kilohertz, 150 kilohertz. Sorry, we are not used to mega. We are only used to giga and tera these days. But but in those days, mega was already big. Anyways, this is the chip, the way when it was done. This is the general purpose registers. This is the stack pointer. This is the arithmetic and logic unit over here, the timing. And the big area here is the control, of the entire CPU. There is an internal bus that goes around like this. Around here is a bidirectional bus that also serves as a memory. And this internal bus connects all the building blocks, and so all the exchanging of information occur via this common bus. The interesting story here is that it was the last one of the 4 chips that I designed. The first was the 4001, and in October, so by April to October, I got the 4001 out. But basically, there were 4 chips designed in parallel, where at the top I had 3 chips that were in different stages of design simultaneously. So it was a lot of work. I worked 80 hours a week for 11 months to get this baby out, actually the entire family of chips. But the interesting thing was that by October, the layout was finished, and that's when I also received the 4001 wafers, and I found that the 4001 worked first time. Then we got the 4003 just a few weeks later, and then the 4004 in November. And by the end of December, I got the first wafers of the 4004. By that time, I had done everything in less than 9 months, which is amazing. I couldn't do it today. I don't know how I did it in those days, but except working very hard, So I got the first wafers toward the end of the year. It was after Christmas, and it was the end of the day, and so I got these 2-inch wafers, and I'm set out to test the 4004. And I was glad that people were leaving the lab because I was so nervous. I was sweating profusely. And so I put the first wafer on the prober, go down with the probes, nothing. Wow. Well, bad chip. So I go to the next one. Nothing. I go to the next one. nothing. Oh, bad wafer. So I put another wafer under, go down, same shit. Bad, nothing. Next one, nothing. Well, not a wafer. Same thing. So finally, I took the wafer under the microscope, and lo and behold, they had left the bury contact mask out for the process. So most of the gates were floating, and no wonder that nothing worked, right? And of course, they were the first time they were using bury contact, so they were not used to this extra masking step. But that way I lost 3 weeks, and though I had plenty to do. But in the second half of January, finally, I got another set of wafers with the proper processing, and same thing toward the end of the day. So I was by myself, and then I came down, and yes, there were beautiful signals in the output pins and the I/O pins. And so I spent most of the night testing, and everything that I tested worked. And so I went home at around 4 o'clock, 4:30 that morning, and Elvia was waiting for me, and I said, "Elvia, it works!" And that there are a few times in life where where you have worked so hard and with such passion, like I did, where you really have a tremendous satisfaction. And it is intimate. It's for you only, because you cannot share that. But it's though I share it with Elvia, but it's really something. It's really something to And I had moments like this also after the 4004, but it's nothing like the first few times. So here. So, by the way, when I was done with the chip, it didn't look like any other chip that I've ever seen a picture of, and I was really proud of it. So I put my initials like a, FF, and that I was so proud of my baby. Oh, let me say it. Okay, now, by the way, this is my daughter holding the first product to ever use a microprocessor. In fact, this is the engineering prototype of the desktop printing calculator that is now in the Computer History Museum. There was a gift by the president of Mr. Kojima of Visicom to me to thank me for taking the thing out of the fire, taking the project out of the fire. And obviously the microprocessor, the key thing is that you can use the same hardware to make different products just by changing the software, and that's obviously that's the value of a computer. But now it was done, so that you can make products that can fit in a pocket instead of having products that are as big as a room. So, and the introduction of the microprocessor stimulated the creation of thousands of new applications, literally thousands of new applications and products that were impossible before if you had to make even integrated circuits, because the cost and the time required to bring the product into the market would be too much. The story of how the chips were put into the market is not well known, but basically because the project was exclusive use of Visicom. So the Visicom has exclusive right for the 4000 family. And I didn't like that at all. So, and also, Off and Mazur thought that the 4000 family was primarily good only for calculators, where they thought that the 8008, of which I will talk about later, would have been good for many other applications. But I wanted to have the 4000 family in the marketplace, and so the first opportunity that I had to show that the 4004 was good also for control application is when I was designing and building a production tester for the 4004. Yeah, because I had to do that too. Do all the test programs, all the testers design and build and so on in those 11 months. So at that time, what I decided was to use the 4004 as the controller for the tester, and also the 4002 as the generator of the signals or the patterns to test against another 4004. So there were two 4002 plus the 4004 plus the 4004 that needed to be tested in that tester. And what I found was that it was actually very convenient. I found that it was much better to use a microprocessor than designing the logic and building and so on. So I proved to myself that jobs like this, which are typical in a company, could be done. And so I started pestering my superiors that to actually get permission to sell the 4000 family into the marketplace. And eventually that happened. And by the end of November 1971, this ad was placed in Electronic News, which was a weekly newspaper on electronics. And this is one of the few ads that where I later accepted that their hyperbole was actually true. Generally you have everybody has a revolution, but this one really was a new era in electronics. And although in those days when I saw that ad, I said, "Oh, isn't it a little excessive?" A paper on this family of chips was published in Electronics magazine in April. Shortly after, a few months after we announced the product in the general public by myself and Ted Off. And that was the beginning of the road for microprocessors. Now let me say a few words about the 8008. If the 4004 is not the first microprocessor because it was limited and so on, well, the 8008 certainly is. It's a real general purpose computer like the 4004, though the 4004 was limited in its addressability of RAM memory. But this one was a chip that came out of a visit by Computer Terminal Corporation in September '69. So 5 months after the visit of BusyCom, they wanted Intel to develop a custom bipolar memory for their new intelligent terminal, which was called the DataPoint 2200. Eventually, CTC changed their name to DataPoint. The terminal was based on a simple 8-bit CPU, which they had done themselves. And it was not much more complex than the CPU of Intel, except by having 8 bits, it would have cost about 1,000 transistors more. Stan Mazur and Ted Off, they told CTC that Intel could actually implement their CPU in a single custom chip. I mean, that took a lot of guts because they didn't know that it was even the 4004 was feasible. But that's how a company becomes successful. You either fall down the cliff or you succeed. So CTC entered into a chip development agreement with Intel toward the end of that year, early 1970. But CTC, without Intel knowing, commissioned the same chip to Texas Instruments also. Texas Instruments, of course, was much more, they had a very major custom design group. They had been at it for many years by that time. And so they were much more experienced in random logic design than Intel was. Hal Finney was an engineer that had worked in custom random logic circuits for another company. Came in March 1970, so about a month before, a few weeks before I joined Intel to design the 8008. So by June, Finney had completed the logic design of the 8008. And by the way, computer architecture and logic designs were well known. The art really to make a microprocessor was more in the circuit design and the layout and in the sort of the proper partitioning and maintaining the speed that is possible with a given process. But so he had difficulty figuring out how to design the chip with the new silicon gate technology because he never used it before. And so the project was suspended. And so in January '71, after that famous night where the 4004 was found to be functional, the project was resumed under my direction. And with the 8080 then, designed using exactly the same methodology, all the circuits that are used for the 4004. So it was a relatively simple project at that point because the knowledge that had been accrued by doing the 4004. The interesting thing is the Texas Instruments completed the 8008 before Intel because there was this big delay from where from June to January nothing was done, but it did not work. So here you go, and it was twice as big as the 8008. So this shows again how much the silicon gate technology made possible really microprocessors because nobody ever heard about the speed, and this chip was never introduced in the marketplace, and so the 8008 was the only one. The 8008 was the progenitor of the Intel 86 family because the 8080, which I will speak about in a second, was based on the 8008. It was introduced in the market in April '72. And believe it or not, the first product was a scientific calculator produced by Seiko that competed with the HP 9100, which was copied by the Programma 101, which was inspired by the little computer that I built at Olivetti in 1961. See how the world turns around? It's actually interesting to view, so here's how it works. So there are many dots that get connected along one's life. Here's the Intel 8008. You can see that the architecture, the way the layout is very similar to the 4004. The general registers, actually this is the stack pointer, the general registers, the ALU, et cetera, et cetera. So it was clearly followed the basic outline of the 4004. Now the microprocessor, though, that really opened wide the market to microprocessor was the 8080. The 8080 was conceived by me in late '71 and architected the chip and using N-channel MOS, which is twice as fast as P-channel. And I also wanted 40 pins instead of the 16 and 18 pins that Intel, the management of Intel, wanted for the 4004 and the 8008, losing unnecessarily a lot of performance. Finally, I won the battle of being allowed to use 40-pin package. And it took me 9 months to get Intel management to let me do this project. But eventually, I got it done, and it started in late '72, and the chip became commercially available in April of '74. It had 2 microsecond instruction execution time, about 5 times faster, actually 6 times faster than the 8008. Part of that 6 instead of, it should have been probably 3 or 4 times, but the rest of it is because of the use of more pins, so you can do more parallel execution. And the first personal computer were born using this chip, the Altair 8800 and others. Though it was the next generation, the Zilog Z80 and the MOS technology 6502, they were the microprocessor that opened wide the personal computer area. So this one is the Zilog Z80. By November '74, I said, if I have to fight to get my ideas accepted like I do at Intel, I better start my own company. So that's why I started Zilog, the first company that was entirely dedicated to microprocessor. And I did that with Angerman, they used to work for me at Intel. And also Shima joined us a bit later. And the Z80, which came out of, was the first product, was designed by the 2 of us and was introduced in May 1976. By the way, it's still in volume production. Estimates that there have been anywhere from 2 to 20 billion Z80s actually sold. 2 to 20 is because nobody knows all the ASICs, where the Z80 is actually embedded in an embedded processor. You never know, because unless you have an inside track in a company that uses it, you never know. So it's amazing. It's one of the most successful microprocessor ever. It started with an instruction cycle of 1 microsecond, and really it opened up the way to personal computers. This is the Apple II that was introduced in '77 using the MOS technology 6502. And this is the Radio Shack, was introduced the same year using the Z80. And of course, Apple did a much better job in terms of marketing and you know, in architecting the PC that Radio Shack did. But the PC revolution, of course, continue, and with IBM introducing in 1981 the first personal computer for business, the personal computer evolved rapidly, and you know, the early personal computers, you can only do text and numbers, and that's it. I mean, but you know, in time you could do graphics and color and sound and images and video, and now you don't think much that you can do all the things you can do with something that you have in your pocket. And of course, telecommunication. The first modems, believe it or not, was that were used in those days was 300 baud, 300 bits per second. I mean, can you believe it? And then, you know, then a couple years later, you could do 1,200 bauds. And so just the, you know, the progress in telecommunication, which was possible because of microprocessor, because you now could use intelligence in the telecommunication circuitry, was enormous. And so the PC, of course, became an instrument for work and study found everywhere. But another revolution, a parallel revolution, was the mobile telephone. You know, this is, you know, NTT introduced the first car cellular telephone service in Tokyo in '79. Of course, there was a fundamental invention here, that is the cellular telephone. In other words, to reuse the same frequency over and over and over again, so that you could serve a lot of different customers. And but the first car cellular telephone, the phone was actually a briefcase. You know, it was pretty heavy. You know, that you needed to carry with you. And then eventually it took another 4 years before there was a portable telephone. That was the Dynatac of Motorola in 1983. And the first generation telephones using this telephone were 1G, were analog. Of course, the control inside was digital, because you needed a computer in a telephone to manage the switching of the, you know, of the cells and all of that. So without a microprocessor, this product would never exist. And the first digital telephone, the GMS, was started in Finland in '91. So it took you know, more than 10 years, about 10 years to get from analog to digital. And then by the late '90s, the mobile phone became the electronic product most sold in the world. You know, I'm told there are 4 billion subscribers of mobile telephone in the world, which obviously means that there are many people that have more than one subscription. You know, one for business, one for home, for example, and so on. And later, but you know, I'm only talking about the early days, the mobile telephone and the computer and the personal computer converged into something like this. And now you're used to something like this, you think, well, what's the big deal? Well, you know, this thing is about 10 times more powerful than the 7090 computer. It has, you know, hundreds of times more storage of the largest configuration of the 7090 IBM computer. They use over 100 square meters of space.
And there's a camera.
Oh, 2 cameras. one to look at you and one to look at the other. You know, why not? I mean, you know, I mean, just think about, you know, I mean, a VGA camera today is about 1.5 millimeter cube. 1.5 millimeter cubes. On one side, it has solder bumps to put it into the PC board. On the other one, it has the optics. The whole thing, the entire camera, that is both a camera and a video camera, and it costs $1. And it's done all by wafer scale processing. All the lenses are all, you know, they're put at the wafer level, and then you cut out the thing, and you test the camera and throw away the bad ones, and hopefully there are not too many, and you've got a product. So, I mean, it's amazing. And in late 90s, Kodak was still thinking the film was going to reign supreme in this world. I mean, unbelievable. What is unbelievable is that people that are actually in the business are so myopic they don't see the power of microelectronics, what is actually happening. Anyway, so another important product is the microcontrollers. The microcontroller is really a computer on a chip. In other words, you have both the CPU, the ROM, the RAM, and the I/O all in a single chip. That's obvious. That's obviously limits you because it limits you to whatever resources you have in one chip. But for many applications, that's good enough. And the first version of this was in 1971. It was a single chip calculator done by Texas Instruments. It was you had to stretch to call it a microcontroller. In fact, the first microcontroller that is justifiably so is in 1974. That's one that could be used for other applications than just a calculator. And, but TI properly was the first to bring into market a microcontroller. I wanted to do at Zilog, my first product was was supposed to be the Z8, which came out 2 years later, but then I opted for the Z80 as a first product. And the Z8 also was a very successful microcontroller that is still in volume production today. So, but anyway, this microcontroller was initially specialized to produce small calculator and became general purpose. And the first modern microcontroller was the Intel 8048 in '77. So, I mean, I don't need to go through, the applications of microprocessors are so huge, and microcontrollers are everywhere. Basically, it's almost a 10-to-1. There are 10 microcontrollers per one microprocessor sold, at least. Many microcontrollers, in fact, more than one, are in ASICs that people use. For example, in the touch screen here, there are probably 2 or 3 microcontrollers just for the touch screen. And by the way, that's another invention that we made at Synaptics that changed the way, first the touchpad for the notebook PC, and then the touch screens that changed the way we interface with our computers. So it's an interesting thing. A luxury car has about 70, 75 microcontrollers. You don't keep track of them anymore. I mean, just they're there. So who cares? I mean, do you keep track of transistors these days? When I had my first AM transistor radio with 7 transistors, I keep track of all the transistors, but not anymore. So let's go quickly through the progress every 5 years until the mid 80s to get a sense of how fast microelectronics has been going, and that progress, by the way, has continued to this day. So here's the 4004. You have 7 micrometer lithography, 12 millimeter square chip size, 2300 transistor, about 200 transistor per square millimeter, 4 bits. 11 microsecond instruction cycle, 15 volt supply. Look at that, 15 volt supply, 16 pins, 750 milliwatts. 5 years later, the Zilog Z80, N-channel with depletion load, 5 micron lithography, about twice the size of the 4004, about 10,000 transistors, about 400 transistors per square millimeter, 8 bits, 1 microsecond, 5 volt supply, 40 pins, 1 watt. 5 years later, the Motorola 68000, N-channel with 3.5 micron lithography, 44 millimeter square of chip size, again, twice as much, more or less. 16 32-bit words, half a microsecond, 5 volt supply, 64 pins, 1.5 watts. And by mid-80s, the Intel 8386 CMOS technology. So this was the first CMOS technology microprocessor at Intel, and used 1.5 micron lithography, 42 millimeter square chip size, so it was relatively small, 230,000 transistors, 32-bit words, a quarter of a microsecond instruction cycle, 132 pin, 2 watts. Today, of course, you have 5 billion transistors, 130, 170, 180 watts in the, in the big microprocessors, and 64 bits. It's at many cores. I mean, just, still in these days, you had 4 clock cycles per instructions. Today, you have many instructions per clock cycles. I mean, that's how incredible the progress has been, and it will continue. So, in 59, there was the year where the IBM, the first computer with transistors came out, and also the year where the planar process was invented. So that was the critical year, because the planar process, as I mentioned, is the seminal technology that made possible all the progress in microelectronics that we had talked about. Just for numbers, the 1790 had 2.2 microsecond instruction cycle. It only used 100 kilowatts of power. It cost 24 million today, more than 100 square meters. I have more storage in my pocket than all the tape drives, and in those days there wasn't even a disk drive yet. But all a room full of tape drives. I have 64 gigabytes in my pocket. And this thing, it took millions of dollars just to store, of the order of a couple gigabytes. And 30 years later, so that means at the end of the 80s, with the planar process and all the evolution of that process, a desktop computer that is more powerful than the 1790, consuming 1,000 times less and costing 10,000 times less money, was available. And of course, today, you know what you do with computers and telecommunications and control and everything else that goes along with it. So this is the power of simple ideas. Thank you, guys. Yeah.
So, I mean, you're already coming to lunch, so your question can't be active. Oh, okay. Thanks for a great talk. I mean, in your talk, you already mentioned that the Moore's law is slowing down, right?
Yeah.
So, how do you think that changes the landscape of computing and even for students who are, in this field?
All right. So, the Moore's law right now is about the doubling rate is about every 3 years, and however, there is a new strategy that is available that has started a few years ago, and that's making more than one, stacking chips. Okay, so up until now, the reduction of size of the transistors has been the primary strategy to improve, to put more transistors and provide more speed and so on. So by scaling. Today in production, you had 22 nanometers. The limit of the MOS structure as we know it will probably be around 5, 6 nanometer. I don't think we can go much beyond that with, with the technology that we know. There are other ways of doing it. And so that will take us to probably 2030, so where you can still make smaller transistors. But now we're making, we're going in the vertical dimension. For example, the 64 gigabyte thing that I was telling you before is actually 8 chips, one on top of each other, okay? All fitting in a 1.4 millimeter thick package. So I mean, that tells you, basically you get about 10 mils per chip. They are thinned down, then wafers on top of each other. I mean, it's a technology that is being developed as I speak. We'll end up with probably several hundred chips, one on top of each other. So the real limit is really power dissipation. And power dissipation, there is no way around that other than, of course, using architectures that are done properly. So that will push people to, for example, asynchronous computers, because a lot of the power is dissipated in the clock circuitry, in the clock system that you have. So if you take the clocks away, you have a much better chance. But then it's just, so that will carry us another probably 40 years So don't worry about it. You know, I mean, you'll retire. You'll retire, and it will still be going on. However, but there are many more things. There are many more things. Have you ever thought about biological system? I mean, you take a paramecium. A paramecium is a one cell. Okay. If you take a little movie of a paramecium in his environment, he happily swims, avoids obstacles, finds food, finds mates. I mean, Jesus Christ, he hasn't got it. He has no brain, one cell, no nervous system. How the hell does he do that? Well, I'm actually convinced, of course, many people would not agree with me, that there is quantum computation going on inside that cell. You cannot explain how you can do this thing. And of course, already people are beginning with quantum biology. That's a new area that is emerging right now. That there is, you know, the superposition is what allows to, you know, living cells to actually achieve the incredible feats that they do. For example, if you take, you know, the photosynthesis, the efficiency of photosynthesis is 98%. 98%. I mean, if you know, a silicon, you know, cell will probably top at 27. You know, and if you do 3,5 material, you get to probably 45%. That's about it. 98%. And there's been a study in a paper that I read, was in Nature a few years ago. Basically, they explain that through superposition they achieve this. Essentially, a photon arrives, and in a way, a photon is in several places at once, and sort of figures out the best place to land to give its energy, and convert that energy into, you know, into sugar eventually, right? So I mean, this is what's going on. So we have 100 years in front of us of incredible progress, just by looking and copying what nature has already done. So
Moore's law will be uplifted.
Moore's law will go on in different incarnations. But even with the current incarnation, we still have about 30, 40 years to go before we begin to really slow down, because, you know, 3 years doubling will be maintained for a long time now, because we can stack chips one on top of each other. Then eventually, you know, it may go to 4 years doubling rate and so on. But then eventually, you know, biology will come to the rescue, and then you don't even have to make a factory. You know, you just allow a computer to reproduce itself. I mean, you're done.
Carla.
Yeah.
How long do you think we have to wait until we have built a computer machine that we can clearly claim is conscious?
Oh, conscious. Oh. I think. You know, I'm one of those guys that do not think that consciousness is an epiphenomenon of the operation of the brain. I thought like everybody else like that, but I have been studying first as an avocation, now as full-time, the nature of consciousness, and I'm convinced now that consciousness is a fundamental property of nature. The energy of which everything is made. The energy of the Big Bang is conscious energy. That energy has consciousness within it. It's a generalized consciousness. Then it needs to, as it specializes, it becomes the consciousness eventually that we have, as, you know, as is at the level of the quantum computation. But the quantum is at the level of the, not of the quantum, is at the level of the Hilbert space, kind of. You know, it's not at the level of the collapse of the wave function. That's the physical world, okay? The consciousness exists like in the Hilbert space, or some space which is, you know, which we, we model with the Hilbert space of quantum physics. So that's my idea. So if that is true, you know, a conventional computer, a Boolean computer, will never be conscious. Now, quantum computers may or may not. In other words, quantumness will be necessary, but perhaps not sufficient condition to become conscious. Now, we can build, if we use biology, which, if I'm right, also use quantum, in a fundamental way, quantum processes, then we may be able to have conscious systems. But then we had to give up the idea that they are deterministic. See, a Boolean machine is deterministic, but a quantum computer, a quantum system with consciousness will not be deterministic. So you have to give away the idea that you have something that you can kind of go this way and it will obey you. It will not do that. It may go that way too, you know. And so that's, you know, in other words, consciousness goes together with free will. It does not. You cannot take, you know, you cannot take consciousness and bottle into a machine, deterministic machine, like a computer. So no computer, the way we know computers today, can be conscious.
Pretty big trade-off if it gets to do what it wants.
But you see,
I think it's I happen to agree
Yeah,
that it's in an interesting direction. But
you
the
got
idea that I can no longer command it is a little bit frightening.
absolutely, and that's why we need to be careful what we do. I mean, we need to be careful. I mean, you know, we talk about cloning human beings. I mean, are you kidding? Are you crazy? I mean, what are you doing? You're playing with fire. I mean, in other words, there is a moral imperative here that we need to be extremely careful, because science, you know, has arrived to a point which surpasses our ability to, you know, to sort of, you know, our sort of spiritual development in a way. You know, we're spiritually behind the technology, our wisdom as a collective. Obviously, you know, maybe the science that develops something is, you know, knows that it would never use it that way, but then it goes in the hands of a military, you know, guy that wants to use it to kill people, and then what do you do? I mean, so we have to be very, extremely careful, because the next 100 years are years that are important for the transition from a type of mindset to another type of mindset. That's why I study consciousness, because if I'm able to convince people that consciousness is not an epiphenomenon of the brain, therefore we are not machines, okay? That would be a great service, because if you think that you are a machine, you're going to act like a machine. But if you think that you are more than a machine, hopefully you act like a spiritual being that has also, you know, a body which is in large measure a machine, but is a machine that we don't yet know, the machine part. And the part that it really makes us human is the part that is what I call consciousness. That's the part that has free will, the part that can understand. Have you ever, you know, do you have computers that understand? They don't understand anything. They just, that's it. I mean, you know, even if they respond to you like they look like conscious, because you have programmed it cleverly to look like conscious, they don't understand anything. They're just dumb idiots, you know. So, but we understand. Have you, you know, you study, right? You study physics, and you know, and you can repeat the lessons. It looks like you understand. The professor may even give you an A, and then a year later you say, "Oh shit! Now I understand what he meant." Wow. Has it ever happened to you? I mean, it happened to me many times. You know, where basically something that seemed to, you know, that I understood only superficially. But there are many levels of understanding. Consciousness is essential to get to an ever-increasing understanding. And I call that comprehension, because comprehension, you know, the field that you connect the dots increases. All of a sudden, wow, you have a different understanding than when your understanding is only very limited. So consciousness has the ability to translate information into sensations. There is no physical phenomenon that we know that can do that. How do you take electrical signals and produce sensations, like the sensation of sound, the taste of wine, the light? How do you do that? Nobody knows. They're called qualia. The philosophers, you know, use the word qualia to express that particular aspect of consciousness. But that is only the beginning. Consciousness is not about qualia. It needs qualia, it's necessary. But out of qualia, which is like a multidimensional display where you have all the experience of your environment in this multidimensional display, you use that first, how to say, display of meaning because it's relative to you, and you make sense of that. You understand that. And based on that understanding, you make decisions that are going to affect your life. And those decisions are free will decisions. So you have qualia, or sensei perception. You have understanding. You have decisions, which are out of free will. And then you have identity. You identify within yourself as yourself. You know it's you. And your experience is an integrated experience of everything which is about you. That's consciousness. That is, a computer has no identity. Computer says, "Oh, that's me." No way. I mean, if it does that, it's just faking it. But you know that you're not faking. You know you are you. That's you cannot get a machine to do that. So that's what consciousness is. The way I look at it, in my own purview. So.
Did that answer your question, Carl? Absolutely. We're just about out of time, but I want to thank Dr. Fajin for both an interesting talk and